In our previous step, we have applied or converted our conventional translational system diagram into a nodal diagram over here. And after we have formed that nodal diagram, we have got, this is our circuit diagram over here. And how to form that diagram, please do follow our previous part of the video. I have already shown you or analyzed this portion over here. Now we do require to apply the D'Alembert principle on this given nodal diagram over here. And what is the D'Alembert principle? The D'Alembert principle is quite naturally the applied force, which is that I am applying over here, plus our resistive force, the summation of these two opposing force, that will become the zero. Because ultimately, after we have applied that force or resistive force, the summation of these two opposing forces do require no moment over there, which means that the structure or that the system do have the equilibrium on the given consideration over here. So applied force plus resistive force, that will ultimately zero. This is the definition for our D'Alembert principle over here, and we do require to apply this D'Alembert principle on our node 1 and 2 over here. Say the left hand side, this is being considered as our node 1 and this one is our node 2. Now if you do apply the D'Alembert principle on our node 1, what is the equation or what is the given differential equation over here? Let us find out over here. So this one is being considered as our differential governing equations over there. And if you do apply the D'Alembert principle on our given node 1, what we have got, the equation seems to be our applied force minus our M1 d2 x1t divided by dt2 minus our b1 d dt of our x1t minus, just go for our in middle part over there. Why these are minus? Because these are our resistive forces elements over there. So applied force plus resistive force. And why do I consider these forces as negative? Because it is actually the direction of that resistive force is opposite compared with our applied force. Because of that resistive force, as it is actually preventing the applied force, the direction of that resistive force will become negative. Okay. So applied force minus our resistive force of mass block of M1 and then B1, and then go for the common part in between our x1 x2 over here, as we are considering 1 as our reference factor, because if you do apply the D'Alembert principle on our node 1, we do consider that x1t will be greater compared with our x2t. So for that one, we can say that minus b2 d dt of our x1t minus x2t, as we are taking 1 as our reference node in this case, which is d dt of x1t minus x2t. And for the last part, we do have the k1 over here, which is minus k1 multiplied with our x1t minus x2t. x1t minus x2t, that will become 0. Now if you do apply the D'Alembert principle on our node 1, we have got this fast differential equation or fast differential governing equations over there, which is the applied force minus all those things are resistive force, which is M1 d2 x1t divided by dt2 minus b1 ddt of x1t minus, as you can see that these two elements of b2 and b1 are placed in between our x1t x2t. And quite frankly, if you do take that one as a reference in this case, as we do have realized that at this point we are applying the D'Alembert principle over here. So quite naturally x1t is greater compared with our x2t in this case, which is that is been reflected in our given equation, which is minus b2 d dt of x1t minus x2t minus our k1 x1t minus x2t, which is ultimately becomes 0. So this is our first equation if you do apply the D'Alembert principle on our nodal 1. Now similarly we should go for the node 2, if you do apply the much needed consideration, or if you do apply the D'Alembert principle on our node 2, what we have got? So this one is, if you do apply the D'Alembert principle on our node 1, for our node 2, what is going to be the equation? Let us to write down over here. So first comes our mass block, which is minus M2, because you can see that at node 2 there is not a single applied force over here. So all those forces is negative, or the negative in magnitude over there, which is quite naturally minus M2 our d2x2t divided by dt2. So M2 has been completed, minus b3 d dt of our x2t, ddt of x2t, minus, once again, minus k2 x2t, and now go for the common part over here. In this case, as we are applying the D'Alembert principle on our node 2, we should take or consider that the x2t will be greater compared with our x1t. So for that one, or for that sake of that consideration, we do have minus b2 d dt of our x2t minus x1t, as in this case we are applying the D'Alembert principle on our node 2. And because of that consideration, we do have the minus b2 d dt of our x2t minus x1t, and last but not the least, minus our, once again, minus k1 our x2t minus x1t, x2t minus x1t, the summation of all these resistive force elements, that is nothing but 0. So in this case, I have realized that as there is no force that has been present while applying the D'Alembert principle, so all these elements, or all these force elements, are quite naturally the resistive force elements over here. Now if you do transfer that minus, or take a common of minus and do transfer to the another side of our equation, all these minus will become plus. So this will become plus, 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 and of course plus. So this is the point for my consideration. And in our next step, we are trying to apply the Laplace transform, which is our step 3. So this is our step 2. So let us do analyze our step 2 once again. First, we have applied the D'Alembert principle on the node 1. So applied force minus all those resistive force that is directly attached with our displacement element of x1 over here. So first, the m1 that is being connected over here. Similarly, for that one, the v1 is connected over here, and all these are our resistive force elements over here. And quite importantly, in between our elements, in between our x1t, x2t, we need to consider that as we are taking x1t as our reference factor over here, which is b2 d dt of x1t x2 minus x2t. Why? Because we are taking 1 as our reference factor over here, which is b2 d dt of x1t minus x2t. Similarly, for our k1 also minus k1, as we are taking 1 as our reference factor over here, which is minus k1 x1t minus x2t, which is becomes 0. Similarly, if we do apply the D'Alembert principle on our node 2 as well, we have got all those elements do have the negative values over there. So m2, because of that m2, we do have minus m2 d2 x2t divided by d2 dt2 minus b3 d dt of x2t, because the b3 is being present over here, and for our k2 we do have minus k2 x2t, and for that common factor over there we do have minus b2 d dt of x2t minus x1t. Why x2t minus x1t? Because in this case we are taking 2 as our reference factor, just by applying the D'Alembert principle on our node 2, which is been reflected in our given equation, which is b2 d dt of x2t minus x1t, and for that last part we do have minus k1 x2t minus x1t over here. So this is our step 2, just by applying the D'Alembert principle on our node 1 and node 2 over here. In our next part, we do require to apply the much needed consideration for Laplace transform to convert our time domain equation into a Laplace transform domain over there, because according to the definition for our transfer function, the ratio of our Laplace transformed of output divided by input, That is the exact definition for a transfer function. We cannot apply the Laplace we cannot apply the transfer function on the time domain analogies over here. So we do require to convert our time domain into Laplace transform domain, and then do require to form the ratio, which is our output divided by input. That is a much needed way to have the transfer function over here. That will be reflected, or that will be described by me in our next step. I hope you have understood our total point for our consideration. If you still have any doubts, please let us know in the comment section for better understanding. Do like, do share our videos, and keep following our channel. So just wait for the next one.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.